Today we will discuss about the array design. So basically we talk about all the memory technologies so far, and we focus on the memory elements mostly. And then today we're going to spend some effort to discuss about the peripheral circuits for the array design. So we will start with the subarray, and then we'll talk about the key modules in the peripheral circuits. So this is a generic memory array architecture. So here we show one subarray. The subarray means, the smallest unit where you have the break of the word lengths and bit lengths. So here we show the 2D array of memory cells. Of course, we have a 3D NAND flash. We talked about earlier where you have a 3D netlist. But in most cases, we have the two-dimensional arrays. And then you have the memory cells, either SRAM, DRAM, or emerging memories, the 1T1R or the cross points. So here, the array, is made of word lengths and bit lengths, word lengths and bit lengths. And then each cross point will be the memory cell. Maybe you have the transistor there as a selection and element plus the memory cell. So here then around the array, we will have several modules for the peripheral circuitry here. So here, for example, we have the row decoder to decode the row address, and then followed by the word line drivers. Because here the decoder is to drive along word line, and then you need to guarantee the timing for the word line and charging. Therefore, you may need some drivers to speed up the signaling across the word line. And also on the bitline side, here we may have the bitline marks, because here, if you do not read out every column at the same time, you can share the sense amplifier with multiple columns. So then you need the marks to select which column you want to read out. And then the signal will go to the sense amplifier, and then we'll talk about that in more details later. So after that, then maybe not all the results from the sensor amplifier will be needed from the external I/O. Therefore, you need another marks to select which bits are needed to be sent out. So here, then there will be like a input and output driver circuitry there as well. So in some of those memory cells, for example, we talk about that in the SRAM, DRAM, you may need some, pre-charge and equalization circuits. For example, SRAM, you have the bitline bar, right? You need to pre-charge both to be VDD to start the read operation. So this is a generic architecture, and then let's talk about some of those key modules. So decoder first. So decoder, you will need both row decoder and column decoder for both word line and bit lengths. But no matter which, then you will have this kind of a decoder structure. So it's a standard digital circuit you may have learned from your VLSI classes. So here, for example, here if it's a 2-bit address, right, then you have the 2 bits, the MSB, LSB, and then you have the complementary a signal. Of course, you can have another like inverter to generate that complementary signal. And then you will have this kind of a NOR gate to decode this 2-bit input to the 4-bit output, or let's say four outputs. Okay, not 4-bit, I mean 4 outputs. So here you can drive word line 0, 1, 2, 3. And those NOR gates, okay, you can use standard NOR gate implementation, right? In CMOS, you know what is NOR gate, right? So this is a 2-input NOR gate, and in CMOS, you know what is NOR gate, right? So right. You have an NMOS pull down, and then PMOS in series, right? As a NOR gate. NAND gate is just the other way. So then the thing is that in the memory circuit design, you could use non-CMOS version of that. Okay, of course you can still use this fully CMOS version, but then to save some area, there are some alternative designs you could choose. For example, here, this one is like with a single PMOS node, right? So here instead of, because in the memory circuit design, right now we only show 2 bits, okay? But if you have many bits decoder, right, then your pull down will have many parallel paths, and then your pull up will be quite a few transistors in series, right? If you do CMOS, fully CMOS version. So that will bring a lot of overhead. So one alternative design is that use just a single PMOS as a node. Of course, then the pull down still is like parallel, NMOS. But then for the PMOS, this is like a PMOS node, and always turns on here. So this will not be a fully like real-to-real logic. There will be some static power consumed by this circuit. But the benefit is that you save some area, right? Instead of like N transistors in series. So here you just use one PMOS. And also you can do the dynamic logic, okay? So here with the clock control, you can pre-charge this node, right, with the clock. And then you based on the decoding result, then you can discharge from this node. So you can use a dynamic logic if you have to gate control instead of the static decoder. Dynamic logic, typically can run a little bit faster, right? So, but still, the CMOS design is pretty widely used as well. Okay, if the input is just a 3-bit, 4-bit, if you have like 6-bit, 8-bit, then the fully CMOS design will be really big. So to address that issue, so typically people will split this into 2-stage decoder. If your input address bits is none, let's say you have this 8 bits, then you want to split that into 2 stages. So here we just show one example. Let's say if the input is 4 bits, okay, after the decoding, you will get 16 outputs. But if you want to, simplify this, you can do 2-stage. This will help with the area, okay? So you can do the first 2 to 4 decoding. This is a pre-decoder stage. And then after that, you do 2 to 4 decoding again. So you do 2-stage decoding. So here the input 4 bits, and then you have the NOR gates, and then you decode first stage, and then the output of that becomes the input of the second stage. So for the large memory array, this pre-decoding is always needed. Okay, for example, your memory array, if typically larger than say 128, 128 is already 7 bits, right? The 7 bit you may want to, let's say 256, 8 bits. For sure, you want to do this 2-stage decoding. Otherwise, 8-bit input to a logic gate will be huge fan-in. This is not good. Okay. So here are just some design considerations for the decoding. So it's standard CMOS digital circuit from your VLSI, but here applied to the memory design. And then let's continue. So after the decoding, as I said, so you will have many word lamps. So typically before you drive the word lamp, because word lamp will be very long, and you have many columns, right? So the word lamp will be long. So then the signal here needs to propagate through the word lamp. It's like you have a big node, big capacitor node here. To ensure the delay is, meeting your timing requirements, then typically after the decoder, you need a few stages of this driver. What is driver? Driver is inverter chain, right? In your digital circuit, to speed up, you have to use driver, size up the driver, inverter size to speed up. So here, how to design the driver. So, you know, in your digital VLSI class, you may have learned the logic effort and so on, right? There is an optimal way to design the number of stages and also the size of each stage. And if you follow that principle from your VLSI class, then if you optimize for the latency, then you may split into quite a few stages. For example, here, if you drive a capacitance, that's unit capacitance, like 4,000 unit capacitance. Then here you split into these few stages. And here this number represents the sizing of this inverter in terms of W over L. Okay. So you see here, if you want to drive with very large capacitance, you need to have quite a few stages. And then the total area will be quite large. So here this unit means unit inverter size. Unit means this is a 1 unit inverter with minimal inverter with minimal W over L. That means 1. W over L is 1. So here you need many of those units inverter area if you want to optimize for the latency to drive such large capacitance. So in many cases, you know, in memory design, right? So you need to balance the latency and the area efficiency, right? So the peripheral circuits will, you know, degrade your area efficiency. So you need to somehow consider how to balance that. For example, here you can just have two stages here. So then this is more area optimized, right? So in this case, to drive the same capacitance, then the total area only needs 65 unit area. But then the delay, you see right? So here the delay changes from 30 to 130 unit delay. Unit delay means the delay to propagate through 1 unit size inverter. So you trade off between those delay and area. So you can balance those two, right? So for example, here in this design, then you get some intermediate value for the delay, like 80, and then total area actually do not increase too much. So this may be okay. So really depends on your application, right? So if you are designing the high-speed SRAM cache L1, L2, then for sure you want to do the latency optimized design. But of course, in the L1, L2, also the array size is kind of smaller, right? So for example, 32 by 32 or 64 by 64. So then the word line is not that large. That means the node, the capacitance is not that large. So if you are designing for DRAM or even let's say flash memory, then especially flash memory, right? So the latency is not that critical. It's slow anyway. So then you should shoot for the area in that case. So this is just a design trade-off. And then let's look at the column side. So at the end of the column, you will have this max, right? So what is max? Max is to select which column you want to read out to the sense amp. So here, there are two kinds of max design. One is with the decoder, okay? So here you still have this regular column decoder. For example, this is 2-bit input data. You select 4 columns. So you have 2-bit inputs, and then you have 4 outputs. And those 4 outputs will control the transmission gate. Or in this case, Bitline bar, you can have a single pass gate. That is fun. So you can use also NMOS, okay? Not necessary to be the PMOS, so could be NMOS. Okay, depending on the output, the signal is high or low, okay? If it's high, then you should use NMOS, okay? So anyway, so here you are going to have 4 outputs, but only one of them will be on, right? After the decoder, one of them will be 1. So that means, for example, if this one is 1, then you are going to select this column out. In this case, we have the Bitline bar, maybe for SRAM. So, but in other memories, only one Bitline will be selected anyway. So this depends on particular memory. So my point is that here you are going to use the decoder with this max structure to select the codon to be read out. So this is standard design. Let's say the pre-decoder based, which is this one. You have the standard decoder, and then followed by this pass gate or transmission gate. And then you can also do the direct tree-based max. So in this case, then because here the arrangement of the pass gate transistor is like a tree. Therefore, you can direct combine the decoding into this tree structure. So depending on the data here, you are going to turn on one pass here to the output, which is a sense amp in this case. So I would say for large number of address bits, then this decoder based is preferred. So because here after the decoding, then this part will be simplified, and this part will be exactly the same. You only have like a transmission or pass gates in one row, so it's easier for the routing, and you know the routing of the wires will be easier. So any questions so far? And then for the Bitline, okay, we are going to introduce some RC model. So here, because we want to estimate the Bitline RC delay, okay. So here, ideally, what we want to do is to build a network with RC components, distributed RC network. So here, let's say you have the wire resistance, and then you have the capacitance, okay, of the wire. Because it's a long wire, so you have to use this distributed, segmented, you know, RC model for the wire. And then you have your memory cell, right? Memory cell you can always abstract into a current source plus some, you know, resistance of this current source. Or you can do is voltage source with some series resistance. Doesn't matter, right? This is like a approximation or abstraction of any circuit. You can have current source with parallel resistor, right? So, for example, here we are going to consider the sense amplifier at the end, okay? So then the sense amplifier, before I talk about that, let me show you this first. Okay, so here we have the different notations. Rm is the memory cell resistance. For example, if you are doing like a resistive memory like R1, then this could be your cell resistance. Or even you are reading out the SRAM, then the readout, you know, read pass. You have the pass gate and then the pull down, and then you have the channel resistance there. So you have this equivalent resistance anyway. And then you have the current flowing through that memory cell. Okay. So here, what we care about is the time for the signal to propagate from the memory cell to the sense amp. This is the delta t. So here, if you solve this RC network in an analytical way, this is the formula, okay? So here we have the Rm and also RL. For the sense amplifier, you will also have the load resistance, RL. And then here, the RT and the CT is the total wire resistance. That means all the R together will be RT, all the C together will be CT. So if you solve this kind of analytical equation in your linear circuit class, like undergraduate level, so this delta T will be given by this formula. Okay, we'll skip the derivation, but give you this conclusion. So here you say it's kind of complicated. Okay, it depends on all those parameters, like those memory cell resistance, node resistance, and then the total C and total R of the wire. Okay. So this is complicated, but we can simplify that into the next slides, depending on the sense amplifier's mode. So here, the first is voltage sensing. Okay. For example, if we pre-charge this node and let it decay and then sense the voltage like we do in the SRAM DRAM. So that is the voltage sensing. Okay. What does that mean for the sense amplifier? If it's a voltage meter, right? You are measuring the voltage here. The ideal voltage meter means what? Means it's open circuit, right? So here, you are measuring the voltage. You measure the voltage here. That means here this node is an open circuit, ideally. That means this RL goes to infinity. Okay. RL goes to infinity. So in this equation, so you can see that RL goes to infinity. So this one will dominate. This one will dominate. So this entire thing will become 1, right? It's infinity divided by because other terms doesn't matter. So it's infinity divided by infinity, and this will become 1. And then this one will also become 1, right? So then you can simplify that. It's just this one plus this one. So then this delta T will become this. Okay. Right. That means voltage sensing. So then let's look at current sensing. Current sensing, on the other hand, means you are going to measure in the current here. An ideal current meter will have 0 node resistance, right? Because you don't want any resistance of your instrument to, affect the current. So ideally, this should connect to the ground. So that means this goes to 0. RL goes to 0, then you can, this becomes 0, 0, 0, 0. Then you can rearrange the terms for the rest. Then it will become this one. Okay. Right. So voltage sensing versus current sensing. And later we will show some transistor schematics to show you what is a real circuit, how the real circuit look like. But here from the abstraction, right? Then you understand to approximate the voltage, the sense amplifier, you just need to know what is the impedance from this sense amplifier. For the voltage mode goes to infinity. For the current mode goes to 0. I mean, in the ideal case, of course, with real transistors, you could say, okay, the impedance goes large or small, right? It won't be perfect infinity or 0 because you still have some transistors in that path anyway. Okay, so you have the two formulas. And then here are some old example. If you take the numbers from this old paper, which talk about how to design the sense amplifier for the S1. This is an old paper. So then the parameters there, if you take, you can plug in the numbers. For example, the memory cell resistance, 2,500 ohm, total wire resistance, like 250 ohm, total wire cap, 2 picofarad. If you plug in the numbers here, because in those two equations, you only need those 3 numbers. Okay, you just plug in, then you get those values. The voltage mode, you need like 5 nanosecond delay. And then the current mode, only 0.2. So it seems that current mode is faster. And the conclusion is generally true. Okay. Of course, depending on the numbers, the specific numbers. Okay. But in most cases, current mode is faster. Okay. But it's more difficult to design with the current modes. And you may spend more transistors in the sense amplifier if it's current mode. So here we talk about sense amplifier. So let's focus on this one because this is a key actually because other modules are pretty standard, like decoder, mux, nothing new, right? So, but the sense amplifier that really could be different for different memory technologies, and there will be new designs for new memories as well. So the memory design, the key is, the memory's peripheral circuit design, the key is the sense amplifier design within the array. And of course, outside the chip, the I/O interface circuit is the key. So those two are where the innovation comes from. So if you look at the ISCC papers, if you want to publish in the memory a subcommittee, then you have to innovate either on the sense amplifier or the I/O interface. So let's look at some simple sense amplifier design. So here, this one is a very simple sense amplifier. And this one, you could use this for the SRAM, but SRAM actually use even simpler one, the latch-based. If you recall what we discussed in the SRAM, just a latch-based. But if you want to do a real like a differential amplifier, then this is a simplest way you could do, right? You require analog circuit class, then you have the differential pair, and with the sense amp enable, which control this bottom current source, and then the load here will be a current mirror, right? You have the different the current here, and then you mirror this current to here, so you can have the differential pair. So this is a current mirror for the PMOS node. So this is pretty standard analog circuit design. So here then you are looking at the difference between those two voltages, right? Voltage mode. This is voltage mode. Why is voltage mode? So because the voltage, goes to the gate of the differential pair, right? Yeah. The gate can only detect the voltage difference. The gate does not really, pass the current. So you always need the reference. If this SRAM, naturally you have bitline bar, but if it's other memory, you only have one bitline, you need another reference voltage here. Or in the DRAM case, you borrow that from the other, depending on the architecture. Open bitline, for example, you borrow from the adjacent array. So you need the reference. So here, this is latch-based, as I mentioned earlier. So actually, typically there will be a PMOS also control as well, the sense amp enable bar. But basically, you pre-charge this, and then you turn on this, then this will flip. We discussed this in the SRAM. I've skipped that. Okay, so let's look at the current mode versus the voltage mode. There was a good review paper from the JetCast from Professor Mengfan Cheng. He's a domain expert in this field. He's a professor at National Tsinghua University in Taiwan, and also he's now the director of TSMC's University Research Program. So here, for example, here, we have this voltage mode. This is a latch-based assay, actually. So here, this is for the resistive devices. You have the 1T1R, and you have the bitline to pull down the current. Depending on the resistance, high or low, you have large current or small current, right? So then this current, okay, will be clamped by this this one, and then this actually, this is pre-charged. Okay, I will say pre-charged by the V read. You are going to pre-charge this pre-charge. It's going to pre-charge this voltage to be the V read, and then depending on the current here, this V rate will decay fast or decay slowly, right? If it's a large, that's high resistance state, then it will decay slowly. If it's a no resistance state, it will decay fast. So that will be reflected to this voltage. And then here is actually a PMOS. This is a PMOS diff pair, right? So here, this voltage is coming to here, and then on the other side is a reference. So this is a PMOS pair, and then this is like a latch-based node. It's a PMOS pair, and then it's NMOS latch, and it's a latch-based node. It's a latch-based node. So the latch-based node could flip faster than the regular whatever you use. For example, the current mirror we showed earlier. If it's a latch-based node, because of the positive feedback, then it will flip. If there's any difference in the voltage, then it will flip faster. So basically, the voltage difference from this node and this node will be reflected to here and here, and then that will trigger the flip of this latch. Okay. And here is the timing diagram. So after the pre-charge, then your Bitline is pre-charged to the V rate, and then depending on the decay rate, after a certain time, we call the Bitline voltage development time window. Then you turn on the send sample enable. Okay, you turn on send sample enable. In this case, it's a PMOS, so it goes to no. So once you turn on that, then depending on the flipping, then the output node here, the D out will stay or will flip. So this is how you detect the high and low resistance in this case. So three-phase, okay, pre-charge the Bitline, and then let the Bitline decay, and then finally you turn on the send sample enable, and then that will flip. Output node will flip. So here we have the current mode, which is the difference. Okay, so the current mode here, there will be a clamp voltage, and then still here this current will be a rate current depending on the resistance high or low. So here there will be the current mirror, and you can size this current mirror actually to amplify. If the current from the resistor is too small, you can use larger transistor here to amplify the current. Or if the current is too large, then you can shrink the current by playing the sizing ratio there. But anyway, you make a copy of the current here. And then on the other side, you could have the dummy reference. Could be coming from the same like memory array, but you program them, let's say half of the resistance high, half of resistance low. Then you can get an average in between. You can use that current as an IREF reference current. So here then this current will also be mirrored here. So here then you have this kind of a mirrored structure again. But here, why this is current mode? Any idea? Why this circuit is current mode? So the key, okay, to differentiate current mode versus voltage mode, as I said earlier, voltage mode, the signal always go into the gate, right? You look at this here, actually the flipping or this differential pair, the signal, which is the current, goes to the drain or the source. That is a current mode, okay, right? Here the signal, input signal, which is this current copied to here, and this inject to the drain of this transistor. Current goes to the drain of this transistor. So that's why this is current mode. And then depending on this current, then this will be charged up at different rates. And those two node voltage will differ. Therefore, that will trigger this inverter to switch. So if you look at the timing diagram here, so first phase, you are going to basically charge up this Bitline from 0. And depending on the current high or low, you are going to charge up the Bitline differently. But the Bitline voltage eventually will reach to this clamp voltage, which is your V read. Okay. I mean, should be close to your V read. And then you turn on the sense amp enable signal here. Then this circuit will flip. And finally, you will get the output here. After this inverter, you will get the voltage output, high or low. So this is the current mode. This is just one example. There are many more complicated designs there. And if you are interested in this one, you can read this paper. Okay. And also in this paper, it compared, because now it's not approximated like a equation. So here you have the real circuit, so you can run spice simulation. And then you can get the real sensing time as a function of the cells along the Bitline. So here you see that if the array is large, the current mode is faster. Okay. If the array is small, voltage mode may be faster. And also depend on the resistance. Okay. If the resistance you are going to sense is, let's say here, for example, 100K, which is this one. So you see that the break-even point will shift. Okay. So this is like a resistance is 100K, and this is 10K. Of course, the lower the resistance, the faster the sensing, right? Because RC delay. So here, if your resistance is high, I mean the memory resistance is high, then this break-even point between the voltage mode and current mode will shift. But in general, to not design the large array, especially with high resistance or small current, then the CSA current mode will be better. If your memory array size is large, let's say array large, and the cell resistance small, large, that means readout current small, then the current mode will be faster. So any questions? So here it's actually difficult to sense small current or very high resistance because the time will be very long. So that's why in the NAND flash, we talk about NAND flash, why NAND flash is slow. Because NAND flash, we have this series, resistance in the string, right? Each transistor contribute to your R of the memory cell. So the resistance is high, or in other words, the readout current is very small. Typically, it's like in this level, 100 nanoamp. So that's why typical sensing speed for the NAND flash, this is 10 microseconds or above. And the low flash, because the readout current is large, like 10 microamp, because it's in parallel each cell, collect to the Bitline right away. So then the not flash tens of nanoseconds. So here then the key challenge, how to sense the small current but with a faster speed. That needs the innovation in the circuit design. That's why I point out to Professor Chang's another paper. If you are interested, you can look into this paper. So it's talk about some technique to do the fast random read current sampling based sense amplifier for small currents, like 100 nanoamp, but still you can get tens of nanosecond sensing speed. And also one of the key challenges in all the sense amplifier design is to address this offset. So what is offset? Offset is in the sense amplifier, because you have typically differential pair, right? No matter it's voltage mode or current mode, the transistor mismatch, the VTH variation, for example, then we'll have some built-in bias to the sense amplifier, right? So that means for this particular sense amplifier, it always prefer, to sense 1 compared to sense 0. Or let's say the margin, right, is there will be some offset margin. For example, here, if it's current mode, then there will be some offset. So ideally, the reference is in the middle, but then due to the built-in bias, the offset will shift that reference for this particular sense amp. Of course, for different sense amps, then the shift might be different. So that means if your memory cell is very close to the reference, that may different sense amp may tell you different results because of the offsets. Okay, so one of the key challenge of all the sense amplifier design is to address the offsets. Okay. All right, so I think I will stop here for today.